Hello, everybody. My name is Asad Mirza. I'm PhD Accounting in the BME department over here at FIU. And today we're going to be continuing our MATLAB workshop series with MATLAB Image Processing Presentation Part 1. So, what is image processing? So, some examples that are related specifically for BME would be, for example, brain lesion segmentation. You can identify parts of an image for, in this case, prostate. You can identify lesions in the skin that are not the same as surrounding tissue. You can have, for example, mammogram mass classification, retina. You can also do airway leak detection in 3 dimensions. Another popular one would be these nodal calcifications. You can enhance these and identify them. And also you can suppress the surrounding bone so you can get a better look at tissue. And these are all just BME applications specifically. Now, if we're going to talk about image processing, we need to talk about images themselves and what they are. So an image is, at its core, just a small little collection of pixels that have various red, green, and blue values. And if you have grayscale image, what an image is just the intensity value of that grayscale, going from 0 to 255. So it's just RGB in terms of color. So if you take a look at this image right here on the right, this is a full color image. And if you were to break it up into just the red, you can see here that the brightest parts of this image are in white and the darkest parts are just closer to black. So for example, everything that's red in this image, which you can reference on top left, you'll see as correspondingly a different value of white on the right image. Likewise, green, it'll be brighter here than there. And likewise, blue, everything sort of has a little tinge of blue to it, but everything also has a various values for it. Now, if you imagine each of these red, green, and blue images to be a matrix of some kind, then anything you want to do to the first image, so any image processing algorithm you want to do to the first image, you have to do to all 3 images all at once because they're all parts of your main image. So if you want to do edge detection, let's say, you would have to do edge detection on the red, the green, the blue, and then combine them. That gets a little bit too complicated. So instead, what's often done in image processing is you convert to grayscale. Now, there are a couple of pros to this. So one is signal noise ratio. You have more signal with less noise. It's the same features in the image are extracted in grayscale without having to represent the colors. So because generally what you want are like edges, features, patterns, shapes inside an image, that's not color dependent. And that's why you want to convert to grayscale first off. It also speeds up code complexity and speed. So imagine if it's color, it's 3 matrices, 3 times computation. Grayscale, 1 matrix, 1 computation. And then for learning dissemination purposes, it's easier to understand these math formulas and everything if you do it on 1 matrix as opposed to doing it on 3 different ones. And the last reason is that my color is not your color, meaning that all of us, for the most part, can see color, but we see their intensity slightly differently. So it's easier to just deal in grayscale and then go based off of feature extraction than it is to actually compare, oh, this blue here and that blue there, they work by inputting into this formula, and then the output is red here, but then my blue and red might not be your blue and red, and so on and so forth, so it might cause issues there. So with that background in place, first, let's load and view an image. If you want to load and view an image in MATLAB, you can use the imread command, and you must have the image processing toolbox there for this to work. So the input is just the file name, which is the name of the graphics file. And the file can either be an n by 3 matrix, so an RGB, or an n by m matrix, which is just grayscale. And then you take this image that you just read and you feed it into this function called imShow. And this will display the image in a special optimized window dedicated for just showing images. And the last way you can view an image is pass this imread input, the output of this, into imTool instead. And imTool is the same thing as imShow, but it also gives you additional tools for pixel inspection, contrast adjustment, and gives you some information on the images. So let me go ahead and show you guys that. So let's say we want to open up this office_1 JPEG image. And in this case, MATLAB can read JPEG, PNG, TIFF, a bunch of other image types. So if you read this, boom, you have your nice little image right here, and you can see it. The other thing would be to use IMTool. So if I run IMTool instead, now it's just like IMShow, but now you can do things like, for example, navigate this image and then look at the actual values of pixels. So for example, if I were to go towards this computer screen here, you'll see the values of the pixels are getting lighter. And that's how you can really detect transitions in an image. And you could also do, for example, cropping. You can also measure distances inside your image. And then you can also, where is it? Pan around your image, zoom into different parts of it. So it's fairly useful, but I don't really find that much use for it, I guess. I just I use native tools, either in Windows or something, to view the image. Not my cup of tea. And the last one is this thing here, where if you want to convert from RGB to grayscale, you can use the RGB to gray command. And if you do this and run it, you will notice before we had this 600/903 by 3 unit 8. And if I run this, now it's 2-dimensional as opposed to 3-dimensional, but you still see the actual image themselves. So you're not losing any information of the image besides the color, which we don't need to identify objects in the image. So going back to the PowerPoint. How do we change the brightness of an image? You can change the brightness of an image by just adding on or subtracting from the image. Or you can scale the colors on an image by putting a value for C here, where C can be greater than 1 if you want to increase brightness, or decrease if you want to be less than. And a small issue with this is it raises the color of all the pixels in the image. So everything either looks very subdued or very washed out. Not exactly preferred, but it's how you adjust the brightness. How you adjust the contrast, though, the way that you can do it is twofold. One, you can use the power law on the image. So if S is the output image, R is your input image, Y is the scaling. So if this is your image, you would just raise your image matrix to a value of Y, and if Y is greater than 1, makes the image darker. If Y is less than 1, it will make the image lighter. The better way to do this, I suppose, is to use the IMAdjust function in MATLAB. And IMAdjust basically has this formula built in, and the value for Y is gamma. You can ignore the things in the brackets. So if we take a look at it here, if you have your image right here and you add, let's say, 200 to it, you can see here's the normal image. Here's after we've added 200 to all the pixels. And if we have contrast adjustment, you can use IMAdjust, and I arbitrarily selected gamma to be 0.4. And if we do this, now you can see you can better make out things in the background that you wouldn't be able to before. Next thing is histogram equalization. So what is histogram equalization? The idea is if you were to have your image and you were to sample every single pixel and then you array them in a histogram, you'll see that, oh, you'll have certain amount of 10s, 20s, 30s, 40s, 50s, 60s, and so on and so forth, all the way to 255. And if you have a very bright image, you might have a lot on the 255 part. If you have a very dark image, maybe you'll see more on the 0 part. But the point is that you should be using the entire span from 0 to 255 to view your image. And if you don't, then you're going to have an image that's either too dark, too bright, too washed out, because you have too many values in the center. Ideally, all the values should be spread out so you can get an equalized image, which is best of both worlds, so you can see both light and dark things in the image. And in MATLAB, if you want to find a histogram of an image, you can use IMHist and give the input of the image, and this will just give you the histogram, which will look like this on the left. And if you want to do histogram equalization, you can just do hist-eq-im or adapt hist-eq. Both subtly different in how they work. So let's go ahead and investigate this. So if we do histogram equalization here, you can see here we have a fairly darkish image. So no surprise here that we have values mainly closer to 0 for us. And if we want to do histogram equalization, we can run the hist-eq command. And now you can see here the values are spread out across the entire region, and now you can better see the lights and darks in the image. And you can also do adapt hist-eq instead, which tries to not disrupt the original image too much, but instead tries to just bump the values without overwashing the image. So it's adaptive in that sense. Now, continuing on, the next thing to understand is the basis for how to do blurring, sharpening, and edge detection in MATLAB, or really just on images in general. And the idea is you need to understand how image convolution works. So imagine this. You have this red square here that is a height of 1, and its width on either side is 0.5. So in total, it's 1 by 1. And you have this green box here that is sliding from left to right. That's also the same size, 1 by 1. And if you imagine taking the multiplication of this height with this height as it's spanning, and then you plot what the area is, you'll see here that you'll create what's called the 1D convolution for it. So as the image passes through, this will be 1, and then this area increases until it's the same, and then it decreases as it spans over. And that is, in 2 dimensions at least, how you would do image convolution for something in your image. So you create an MIN matrix max. The numbers control what the operation is going to be, and then you just apply it to the image. So for image convolution in 2 dimensions, for each particular pixel in your image, you would take a look at it, and then you would have your mask essentially, and you would multiply the pixel with the mask, then sum up the result and move your way across the image. So this is your input image, this is the output after it goes through the mask. And basically you can think of the convolution as sort of a weighted sum of whatever your input image is. And the best way to understand this is really with an example. So let's say blurring and sharpening. So up here on the top here, we have an example of what a blurring of the image would look like. So here's your mask, and imagine you took this and you multiplied it upon an image. This will be the center pixel, and this center pixel will get the influence of all the other pixels around it. So it's as if it was blurring together the surrounding pixels, and the value is replacing the center. And this is the reverse. The central pixel gets its influence maximized by 5, and the surrounding pixels get reduced to their opposite and even 0 in some case. So this will be an example of a sharpening filter. So you can think of it as low frequency values is like a slow changing pixel. So if you're scanning across an image, pixels that aren't changing a lot are like low frequency. But if you suddenly see a couple of pixels where suddenly the value is really dark or really light, that's like a high frequency change. And what you can do is blurring the image is like applying a low pass filter. So it sort of blurs all the image, all the values are sort of the same now. However, sharpening is like doing a high pass filter. Everywhere where there's a difference in intensity in your image, this is going to enhance that difference. So if you take a look here at this image of these columns here, if you do a blurring of this image with this blur kernel of a new convolution, now you lose detail in the image. If you do sharpening instead, now you can better see these lines and divisions in the image. And that's what I was saying by it being like a low pass and a high pass filter in a way. So how do you do it in MATLAB? 2 ways generally. So you can do the tedious way, which is create a convolution mask and then do conv2 in MATLAB and do A, B. A is the image, B is the mask, and your output would be the convolution result. The other way, and it's better, I guess you can call it, is using what MATLAB has as F special. And F special are basically is basically kinds of pre-built mask algorithms. So for example, if we want to do a blurring or an averaging, we can call average and then specify the size of this mask with n. If you want to do sharpening, you can do unsharp mask and then give the degree of sharpening with a. And then if you want to call this, you do the IMFilter command and give it the image and then the mask from these two. So let's go ahead and look at this. So here's doing it a tedious way. If you had a rice image, let's say, this rice image right here, we can make a mask that's 1 by 9 by 1's 3, which, if you remember, is the averaging kernel. Conto the image, then you apply the mask. And if you take a look here, here's the original image on the left, and then you have the blurred image on the right. Now, the better way to do it is to call f special and then average. If I do this, you'll see that the mask is the exact same thing, but I can control the intensity better. So for example, if I were to do like 4, let's say, and run this, it's a different value. Easier to do than hard coding it. So if I just do standard 3 and I run this, you get the same result, but it's more flexible. So now that we're this far, now comes the question of how do you detect an edge in an image? Detecting an edge is fairly straightforward in an image. If you imagine scanning across an image, and let's say you start off at point A here, and you scan across, then as you scan across this image, you'll see that you'll have a bunch of white values, and then there's a sudden transition. And then you'll have darkish values for the most part, and maybe it'll change a little bit in the center. And then when you reach this edge again, there'll be a sudden transition again. And if you plot this on a graph, you'll have values, transition, values, transition. And this sharp change here is an edge. So how do you actually go ahead and find these edges? Well, you can think of these transitions to be like derivatives. And if you see a very sharp change in these values, then that'll be a large slope. If you don't see a very sharp change, so for example here to here, then that would be like a small slope, so not an edge. And if you remember back in the high school definition for our, I think it was like Cal 1, where you learned this formula, this definition for the edge, where you can imagine f of x being your image. If you take the image, then you take a look at the pixel next to it, and you divide by the spacing, which case for us is 1 pixel, this will be your derivative. So for us, the value of the pixel minus the value of the pixel right next to it, divided by the spacing, which is 1 pixel, and that will be your derivative. Or in other words, you just take the difference between any 2 pixels, and that's your derivative. So you can do a forward derivative, which is pixel minus the 1 in front of it, and that would be your forward derivative. So you can imagine here, that's like applying a mask to your image, where if you take a look from one end to the other, scanning across, the pixel that you're examining is not important, just what's next to it is important. If you see from one end to the other, the value increases, then that would be a positive derivative. If it decreases, that's a negative derivative. If it's really large, then you'll see a very large value. If not, you'll see a very small value, but it'll be directional. So you can have a mask in the x direction, and likewise you can have a mask in the y direction. And if you want to do it backwards, then it will be f of x minus the pixel behind it, and then that's it. If you want to do a central difference instead, you'll look at the value of the pixel in front of it and the value of the pixel behind it, which is what these masks are doing. Now, the way these different algorithms are called in MATLAB and general image processing are called Prewitt and Sobel horizontal masks, which are the most popular. And you can apply them to the image in the same way that we did for the sharpening and blurring masks. And you literally just call IMFilter on this mask, and then you can apply them to the image. And if you want to figure out not just the X edge detection or just the Y, but the overall, you can use the hypotenuse command in MATLAB. So let's go ahead and investigate this. Where, and there it is. So we were here, yeah. Drawing an image. So I might as well also show the sharpening part here. So if you had your original image here, and we had our sharpening mask. You can use COM2. And now you'll see this sharpens up the image so you can better see the transition between the rice particles. And then this is using the IM filter command for unsharp. And you can see this is a slightly different kernel, but the output is still the same. It enhances edges while minimizing non-edges. And just to better show you what I meant by intensities, if you take a look at here, as you're scanning across this red line, you'll see transitions wherever you have an edge. So no edge, no edge, no edge, edge, no edge, no edge, edge, no edge, edge. And then by the time you get to this White House part here, you see a big transition, not too much, and then transitions again. And so detecting these transitions is how you figure out what an edge and what is not an edge. So here are these pirouette masks I was talking about. So if you take a look at it, it's 1, 1, 1, 0, 0, 0, negative 1, negative 1, negative 1. And if you scan across the image, it's going to figure out what's horizontally changing. So if I run just this part of the code, you'll see here that the pirouette has shown you where you have changes in the X. And changes in the Y. So now you can see the horizontal edges more clearly. And then if you run it on the Y instead, now you can see vertical edges more easily. And this is because if you take a look at the filter, as it's scanning across the image, it'll show any transitions between 1 and negative 1. So you'll see vertical edges more clearly here. And if you want to combine this, you can do the hypotenuse, as I mentioned before. And now you get the best of both worlds. You see both horizontal and vertical edges. Now, the better way, quote unquote, is if you instead use MATLAB's edge command directly, and you give it the input of what algorithm you want, and you give it a threshold of what counts as an edge and what doesn't count as an edge. So if you don't apply a threshold, MATLAB just tries to figure out what the best threshold should be for your image, and tries to work based off of that. So now, let me just show it to you here. So we're working on the lighthouse image again. And if you see here, as opposed to what our value was before, now we have distinct black or white images because they automatically figure out what the threshold should be. But you can very clearly see here, you have no edges in the clouds because there's no sharp transitions in the cloud. However, there is a sharp transition when you hit this lighthouse here. So you'll see the edges here, the seams, certainly in the house region, you'll see edges. And if you want to use Sobol instead, and if you want to compare them, might be better. So on the left, I believe is pirouette, and the right is Sobol. So both are edge detection algorithms, but some of them are better than others, depending on what input image you give. In this case, I think they're pretty much the same. But if you go researching each algorithm individually, maybe you'll find which one's better for a given test image or not. But those are the two most popular. And with that, I believe we can end part 1. And part 2 will go into image filtering and then doing Fourier transforms, as well as more direct applications found in the field. But putting that all into one seminar would have taken way too long, and this would have stretched to an hour, hour and a half. So with that, any questions?
Yeah, I think a very popular image processing one for edge detection is Canny.
Yeah, the Canny filter is another one, and I think MATLAB does have the option for it. Canny method, yeah. So Canny is certainly an option that you can use, as well as the Sobol and pirouette, and there's also the Roberts. But they each have their pros and cons depending on how your edges are in your image. And usually it's good to just check them all and see which one works for your application.
True. Thanks.
No problem. All right. Any other questions? I wonder what canny actually looks like. So if I copy this and then do canny instead, let's see how canny works.
Yeah, you can make a montage of the three.
So canny seems to better find the edges in the clouds and more distinctly identify the edges on the house. Pros and cons. All right.
Thanks, Asad, once again for coming here.
No problem.
Stay tuned, guys, for part 2, where we're going to apply even more image processing techniques. And stay safe, fellas.